Welcome to this seminar. Today it's my pleasure to introduce our distinguished speaker for this seminar on geophysics, Dr. Falk Amelung. Dr. Amelung is a professor of geophysics at the University of Miami, where he has been a valuable member of the faculty since 2002. Dr. Amelung's academic journey is as diverse as it is impressive. He has earned his PhD in seismology from Strasbourg, France, and subsequently honed his expertise through positions at Stanford University and Honolulu, Hawaii. The rich background has contributed to his comprehensive understanding of geophysical phenomena across various geological settings. In his current research, Dr. Amelung employs cutting-edge InSAR technology to investigate a range of critical geophysical processes. His work spans the study of active volcanoes, tectonic movements, and land subsidence phenomena. Today, he will be sharing his insights on land subsidence and aquifer deformation, topics of increasing importance in our changing world. Dr. Amelung's expertise in these areas promises to provide us with valuable perspectives on the complex interactions between human activity and Earth's subsurface processes. Without further ado, please join me in welcoming Dr. Falk Amelung to share his knowledge on a recent work he did on coastal subsidence on Miami's barrier islands.
Thank you. Thank you very much. First of all, ignore the title slide. I forgot to update it. That's from a previous talk. I just noticed it. That's what I wanted to do last. Okay, so thank you very much for giving me the opportunity to talk here. So what I'm going to discuss is not necessarily what is on this title slide, but yeah, so I've been doing recently I'm here in Miami since a long time, working most of the time somewhere else in the world. And since recently we are focusing really here on Miami, and that is what I'm going to talk about, and that is related to the condo collapse a couple of years ago in Surfside. And yeah, so what I'm going to do today is, first I'm going to give a very brief overview about some other research, and I'm here also to look for collaboration. So I'm just presenting very briefly something at the beginning where I can use some help if somebody is having some interest in it. Then I'm going to talk about our study on the Miami Beach barrier islands. And after that, I'm going to talk briefly about the mining area here very close to FIU. Okay. So, so what I'm presenting here is mostly from my postdoc, Bazane. She just moved to a different position, but she has done the Miami work. And another important collaborator is Khalid Sopan at FIU, and for the InSAR, some folks in Hanover. Okay. So first, I'm going to come to the other topics very briefly. Yeah, I am spending quite a lot of time actually in the Galapagos Islands at the University of Miami. We are having a teaching program there, U Galapagos. The teaching for that is happening right here in Puerto Villamil. Yeah, so in the Galapagos Islands, Puerto Villamil, I have been working on the volcanoes in the Galapagos since a long time. This one here is Sierra Nevada volcano. It is, I think, the most actively deforming volcano on this planet. With the InSAR technique, about which I'm going to talk a little bit more later in detail, we can see measure the ground deformation, and this thing is at the last eruption 6 years ago, and since then we had 6 meters of uplift. If everything goes right, then in a couple of years it's going to erupt again if it continues with this rate. So that is something at this rate, something what I'm looking forward to. Yeah, so I go there for the field trip field trips with undergrad students, or actually, yeah, teaching a 2-week intensive course about Galapagos geology, and part of it is the field trips. Last time, and that goes now into the science, when I was there, that was in March, April. We had some beautiful sunsets. There's another volcano in the background that is Cerro Azul volcano. So beautiful sunset, extremely red on a volcanic island. Why could that be? There was an eruption on a neighboring island. This is on Isabella Island. The eruption happened in that. So you can't see it. The eruption happened somewhere. There's the other volcano is in that direction, and that was Fernandina. Fernandina volcano also showed significant uplift, something like 1.5 meters, and then it erupted just before I arrived there. And what is different of this eruption is that there's not much precursory uplift. The uplift stopped, yeah, a year or so before, and then suddenly it goes. So why could that be? So this is not very convenient here. Fernandina has a caldera lake. This caldera lake grew pretty rapidly by 15 meters or so in the last couple of years. So what I think is, we have done some other studies on a similar topic. The water plays a role. There was lots of rain. The rock got wet, and then the volcano erupted. The magma chamber broke without any need for precursory. It broke. The dike propagated not because of magma pressurization, but because there was so much water in the rock that it got weaker, and there's failure criteria for rocks which say that the rock can break when it gets wet. So what I'm would like to do is to develop some hydrogeologic model for these type of volcanoes, and in a similar way also for Mauna Loa volcano, another basaltic island volcano in Hawaii, very similar, well, in some respects similar to the Galapagos Islands. There's lots of orographic precipitation. We are having this flank here moving pretty rapidly. That is the site where there's orographic precipitation happening. This site is not doing much. This is here precursory. In the last couple of years, it's precursory inflation, deformation prior to the eruption. But so that is also something what I think hydrology can help if you could make a model for the water distribution there. And yeah, just very briefly, another topic where I'm trying to get a project started, also related to hydrology. In India, we know very well from GRACE data, gravity data, there is lots of water lost in northern Indian area where 400 million people are living, and yeah, with the InSAR technique, this can be studied. So if somebody is having some interest in these kind of things, I would be delighted to talk some more about it. Okay, so now I'm coming to my real talk. As I said, the study was motivated by this tragic collapse that happened 3 years ago in Surfside. Unfortunately, 100 people, 98 people got killed. This is the location. Yeah, right. To the right is the 87th. To the right is the 87th. 87 Park condo. There were construction going on at this big condo to the right, and some people at the time said that could have been partly responsible this collapse. Just to give you a brief overview for something what you probably have seen many times, the geology of Florida. If you, of course, there's no topography, but if you do your shaded relief with the proper parameters, you still can get something what looks like topography in central and northern Florida. But of course, down here in Miami, we have nothing. There is the Miami Oolite, which is the elevated topography, and then Surfside, we can see where it is. It is not part of the Miami Oolite. These are the barrier islands which have some different geology. The Miami Oolite, that is how it looks. That is from somewhere from downtown Miami. In other parts, that is the oolite looks like this, or the limestone. That's rather another typical Florida limestone with lots of voids and cavities. Then we are applying the InSAR technique. This is a satellite radar interferogram Sentinel for South Florida. One color fringe corresponds to 2.8 centimeters of deformation. It could also be delays from the topography. And it's a technique which is around since long. What I'm going to do now is I'm going to focus on the Miami Beach area over here, and the white box indicates the area where the collapse happened. How does InSAR work? It's an active imaging instrument. It's a radar on board. It sends a signal. The signal comes back from a building, for example. The satellite, after a while, comes back 12 days by now, comes back. And if the ground has moved by a little bit, then we can see that. And if the ground continues to move, then we can nicely measure that. What you need is some stable ground. Otherwise, the signal doesn't go back to the satellite, or it's affected by something what we call temporary decorrelation. So you don't get radar signals where you have InSAR data, at least not with this satellite, wavelengths what we're looking at, in areas where there's vegetation. And we distinguish, well, you're getting signals in areas where there's buildings. You are getting, this is what we call persistent scatter arrays. The signal is very strong in frequently it's just a point scatter. We are getting somewhat signals also from flat areas, as long as there's no vegetation. And these are called distributed scatterers. So they have useful signal if there is strong vegetation here where we have the forests, we don't get anything. And then what we do is we combine lots of those images. Actually, 250 in the case of Miami, 230. And we are developing our InSAR time series, or averaged velocities. And it's a very computational technique. So I'm working actually on, not in Miami anymore, on supercomputers in Texas. Running one of those data sets, you need something like 3 terabytes of data. And then it takes a couple of hours, as long as you have enough cores available, CPU or nodes available. And so this is the result. This is for Miami Beach, Surfside, and Sunny Isles, or other way around. Sunny Isles up there in the north, and we don't get data in the water. And so blue is, in our case, subsidence. There is quite a significant signal in Surfside. in northern central surf side and southern surf side, as well as in Bal Harbour in no, this is Sunny Isles. I'm sorry, this is Sunny Isles in the entire Sunny Isles, Bal Harbour and Surfside. Whereas in Miami Beach, there's hardly any signal. So what could be the reasons for those signals? So let me first describe those signals in a little bit more detail. It turns out most of these signals are associated with buildings, with the high rises. And what we see here, if you look, for example, at the residence by Armani Cursor, it was relatively recently built. We see a total of 4 centimeters of displacement, more or less linear. The same, yeah, so some of those buildings show 4 centimeters, 2 centimeters, essentially all those buildings, what are shown here. I don't show those buildings which don't have any signals. There's a couple of them which don't have. They show, yeah, quite a significant signal. And what we measure is distance in line of sight direction towards the satellite, which may or may not be vertical. We don't really have any constraints on it if you just use one single satellite. And yeah, so the temporal signal there is this is the Bentley residence site. There they are they probably have started already to build a new development. What is the signal is, it went down a little bit. Then for some reason, subsidence increased rapidly, and after that, it stopped. What we used for this processing, for this data processing, so we have our own software, which we developed over the years called MinPy and MilePy. But this one is actually done using a different software, Sarway, that is from the University of Hanover. This type of analysis, yeah, so by academia, it's actually not done so much. It's mostly companies who are doing that. Because of the applications for a number of different applications to look at subsidence in oil fields or to look at infrastructure. And okay, so let me focus a little bit more. Yeah, so these are of course beautiful buildings. So let me just give you an idea. The Porsche Design Tower, that is one of the places which shows significant subsidence. Other way around. Yeah, beautiful building. Luxury as it best. You have an elevator for your Porsche. You can park the Porsche right next to your apartment. Beautiful view. Way to go to the pool, the common pool. You have your pool in your apartment, and it's not cheap though. This penthouse, I found this online. It was $32 million, and in Miami, of course, things are expensive. If you have something like that, actually, property tax is two per mil, something like that. But so you have to pay something like 350,000 per year of tax or so. The 11 car garage, I am not really so sure whether it is so useful. If you have your parked cars up there, then it is a little bit difficult. You may have to go 50 stories down to get to one of those cars. But okay, some people want it. And there are some famous residents. Messi, actually, I think now he lives somewhere else, but before he really moved to Miami, he had an apartment there. Okay, that was just a little aside, but essentially all these buildings in well, not all, but later on I come up with a percentage. Lots of those buildings show significant subsidence areas, and some similar signals as we saw before. Here we have 2 buildings. They show subsidence. The total amount is not very much, 2 centimeters, but it's happening at a certain time. So there must be a reason for that. If we go further south, then we come to in southern Sunny Isles. again, so some of those, what this shows is for 2 different time periods. Our data time series starts in 2016. But for some areas, especially if they were built recently, we don't necessarily have data which go all the time back to 2016. So yeah, so for example, here the Ritz-Carlton, it was built in 2019, and well, that's when our time series start. Whereas the Trump Tower above, the time series starts. We have a longer time series, but again, the same signal as for others, something like 4 centimeters or so. And yeah, we go further south. Now we come to Bal Harbour and Surfside, and again, there's a couple of buildings which show a signal. Later on, I'm going to focus in more detail on the Oceana residences right at the top, and on the surf club area here, where we have an interesting signal. And then I come to the 87th Park Tower down here. Here, for example, the signal, not much is happening. Then suddenly we get the subsidence, and after that, subsidence continues, but at the lower rate. Okay, and yeah, in Sunny Isles, 70% of the coastal structures, they show some sign of subsidence. In Bal Harbour, only 3%. In Surfside, 30%, and in Miami Beach, hardly anything, 1 or 2%. There's lots of buildings, and we have 1 or 2 which show a signal. So what could be the reason? So yeah, and so this study is, as I said, we have completed it, submitted, but it's not published. And if somebody has some ideas what we can say, or yes, I'm very open to it and hope to hear it. So something what I'm wondering, yeah, one of our subsidence areas is the Surf Club Hotel, and that was actually the first building which was built in the town of Surfside back in 1935. Now, the subsidence area, so you can't tear down historical buildings in Miami, as you know, but there's nothing what prevents you to build on top of it. So here is the old hotel, it's still there, so they didn't tear it down, and then they built a new one over it. And yeah, over there is the signal, and yeah, I don't know. Originally, I thought, okay, maybe there is was a geologic reason for people to build the hotel right there, and that could be the explanation for the subsidence. But so let me tell you first a little bit more of yeah. So these measurements are tricky. It's not obvious to do, and that is related to the geometry. These residents or these buildings just yeah, vertical 80 meters high. In this case, the Oceana residence, and the satellite looks from this direction. And then when the satellite takes an image, the first pixel, the first return comes actually from the top of the building, and later on comes from either the ground over here or over there, etc. So what we see first is from the point B1, and that is why yeah, it shows up here to the left from where the satellite looks. So what we do then is we can estimate, as long as we have enough data, we can estimate the elevation of a pixel from those data. The scale for the elevation is to the right. And what we found in this case, it's about 80 meters high. So that's great. We have a digital surface model, LiDAR. It shows also 80 meters. So we must have done this right. We're getting the right elevation for the pixel. Then we can use this elevation to correct the estimated elevation to correct the location. And so what we find then is, yeah, as shown here, a couple of those pixels right on top of the building, they are dark blue. That is what we would expect. But if the building subsides, that's what we would expect. But we have a couple of other pixels which are green. That means they don't move. That is somehow surprising. And then if we correct the estimated elevation, also using the estimated elevation so that they are going to be displayed there where according to the estimation they are, we find on the roof, we find a couple of pixels which are red as expected, but a couple of pixels as almost 0 meters elevation. And what I think is happening is that there is this opening there, and you're getting some complex reflection through the opening, and that is probably part of that must be the reason. So you have to be careful. If it is the other alternative is that actually there's differential subsidence on this building, and that wouldn't be good. If you have differential subsidence, then things can break. It took a while that we convinced ourselves that these measurements are correct, and then we use different softwares and different satellites, and we are seeing more or less the same thing. Signals, small, couple of centimeters of subsidence, which later on declines. We are seeing with different wavelengths, with different satellites, though we are seeing different pixels. Okay, so now let me go back to the geology and address the question: what could be the cause of the subsidence? So we obtained some information about the geology from geotechnical reports. These geotechnical reports, before they build one of those high-rises, they do a geotechnical exploration. They drill in there, take samples, test the rock or whatever they find, and then the foundation is designed accordingly. And we were able to get geotechnical report for a few of those buildings, but not very much. And what we see is, shallowly, there is a couple of meters, 8 meters or so of sand. The foundations, it goes through, so, or the piles go through, so it's not necessarily, we wouldn't expect that it's affected. Below, we have the limestone layer, and then we have some more sand. And that was somehow not really expected, in particular at the Porsche Design Tower. So this is here further north, Porsche Design Tower, and this one is somewhere in Miami Beach. Unfortunately, it goes not so deep as the other places. So we are seeing, okay, it looks like in the north there is more sand in the underground than in the south, according to this sparse data. And there is a couple of places where we have information from the USGS, and then public data is just great. They have to they're putting it online in the database. Everybody can go and find them. And one of the places, Stillwater Park, that is at depth 25 meters. That is what we expected. It's just limestone. If you go a little bit higher, there's actually a void, and that is it's a surprise, but that's apparently what the geology is. There are some places where there is nothing in there. Maybe there was sand at some time in the past, and then it has been washed away. If we go to another place, what we see there, we don't see the solid limestone as we would expect. There is quite a lot of sand layers in there. So that is somehow, there is much more sand at depth than we expected. So with that, what could be the cause for the subsidence? So the first thing what comes to mind when you look at subsidence, or InSAR people, when they look at subsidence, is groundwater extraction, but that's not the case there. It's salty. Nobody extracts groundwater right there. The other possibility is consolidation. When you build a high-rise, heavy high-rise, it's observed in many places. For example, in Chicago, close to the Great Lakes, you're putting your heavy high rise on some silty soil, and then of course when the heavy material sits on there, then it slowly presses the water out, and you're getting slow subsidence. And they are designing the foundations accordingly. So that's that is Terzaghis principle. So it doesn't apply to our area here. Another option is natural compaction, maybe under the weight of the structure. But if you have really solid limestone, you wouldn't really expect it. So probably not. And the other alternative is construction related, and that is, I think, what is happening, but we are not sure. So how can you create subsidence from construction? So we are having the sandy layers. There was no building on top of it before, or no heavy building on top of it before, so they are not very much compacted. And then somebody is building something, is vibrating. For some of the construction, there was really heavy vibration at the time, not anymore, which makes it a little bit difficult to understand. You get the vibrations, and then from the shearing, the grains, they move around, they readjust. You get realignment of the grains, and if you have at the same time the load on top of it, then so you're getting subsidence, or that is what geotechnical engineers call dynamic settlement. And so after a while, you may have gotten some subsidence. And vibrations may be one possibility, but as I said, now the construction companies, you don't want to annoy your neighbors too much, so they don't vibrate again. They don't vibrate very much anymore. So another possible explanation could be, and I just don't know what it is, they do some sort of pumping when they do the construction, and then you have flow which goes through the sandy areas, and this flow might cause also realignment, and then if you have the heavy load on top of it, you may get the grain rearrangement, and you have to start this process apparently only once. So the vibrations, for sure, they were not all the time. There were some time period where there were strong vibrations. With the pumping, the same thing for construction. It was pumped and then it stopped. So the process has started, and now it just slowly continues. Okay, so so as I said before, we are having significant signal in the north, in the sunny isle areas. And by the way, this in the meantime, so the processing is tricky. Now we have some results which are not really planned up yet, which show still strong subsidence, but a little bit less. So the areas, it's not as blue as it is here, but nevertheless, it is there's quite significant subsidence in the north, and then less subsidence in the south. And if the sandy areas are responsible, that would work. We have more sand in the north than in the south. How are the temporal patterns? As I said, we have some buildings where we see sudden onset of or an acceleration of subsidence, and then it continues to decay. We see it at nearby buildings. So what might have happened here at the Trump Tower, we see subsidence before the Ritz-Carlton is built. So the accelerated subsidence could be due to the building of the Ritz-Carlton. Regarding, I talked about the spatial pattern, but we know at the 87 Park in Surfside, at the right next to the Collapse condo, there the subsidence is only localized. nothing is happening nearby. But there was some strong vibration. So that is one of the places where we are sure that there was vibration. So that's a little bit, that is somehow a little bit a mystery. We would expect, especially, okay, I forgot to add the results from Shimon. Shimon looked at exactly, okay, I forgot. Shimon looked exactly at this area, and he did find also quite a significant subsidence area, but that was in the back in the 90s. And yeah, so we don't really see that for the current habit, but that was actually part of the reason what motivated us to do this work. Sorry. So now what about the collapsed condor? So as I just said, we have the subsidence to the south and the 87th park, but the collapsed condor, there is nothing. We have a couple of pixels which are on top of the building, but there's just no signal. But we know that there was some precursory decks on the pool deck. But so it turns out the location of the pool deck, it's over here. With the satellite geometry, you just can't see it. The satellite looks from this side, and this is in the shadow. So we don't have any observations there. And you can look from the other side, what we have done to some extent, but not very much. If you look from that side, here at this place, you're getting reflections from the entire building. So yeah, we don't see any signal, but it's not necessarily conclusive. It doesn't mean, well, in the area where we do have proper observations, which is right here, it is conclusive. Nothing happened. But in the other part where the first cracks appeared, we just don't have data. And yeah, as I said before, okay, I'm repeating myself. Right next to it, we do have the subsidence from the 87th park itself. Or only the 87th park is subsiding. Of course, after the collapse, we don't have any data for the collapsed condo because it wasn't there for the collapse. Okay. What about differential settlement and tilt? Yeah, let's go back to the Porsche Tower. For the Porsche Design Tower, we have quite significant signal, 10 centimeters, 11 centimeters. That is from one satellite, which looks from one side, whereas the other satellite, which looks from the other side, is having only 5 centimeters. So there is somehow 5 centimeter. Okay, you're looking from the east, you're looking from the west. There is somehow 5 centimeter. It's must be moving. What about other places in downtown Miami? There we haven't really looked very much in detail. We have quite some signal, but yeah, the study goes forward slowly. Somewhere where you build some high rises, essentially all the high rises have some kind of signal. So what we hope to do, wrote a proposal, didn't get accepted, so we have to try it again, is actually to use distributed acoustic sensing. We use fiber for the internet. There's dark fiber. You send seismics, or you send signals through, optical signals. They come back, and that is something how we could measure actually vibrations and probably the local geology. And if somebody is having some interest in those type of data, I don't know whether for salt water it wouldn't work, but it would give some idea about the geological subsurface. Yeah, if you vibrate, that is what could happen. Granular material is exhibiting some really strange behavior. So when we did this study, okay, so I was really worried that okay, any of those buildings is going to, maybe we're going to have another collapse. Over the summer, I was a couple of weeks in China, in an area where everything was newly built, and I don't go anymore into high rises without having the data processed before that. And there is lots of subsidence, lots of similar. So you have, yes, that's what is happening. If you do construction, you are frequently getting some subsidence. So it is nothing really to worry. It's good to know it, but not to worry too much about it. And then this is something what I got from Mike Zucker. This is one of those residences which was recently built or which is under construction in Miami right now. These foundations, they are really strong. So even if one of those buildings moves a little bit, it's not going to collapse anytime soon. So I don't think we have to worry too much about that. There is an example, the Leaning Tower of San Francisco, the Millennium Tower that was discovered in a couple of years ago. There was a total tilt of 70 centimeters, and it's still standing. So just to give you a little bit of some other cases. Well, what we haven't done, we haven't looked really with the high resolution data very carefully. This is just how one of those high resolution Terrasser X, they have 3 by 3 square meter pixel size, how it looks like. The satellite flies in that area, and the first returns what you get is over there from top of the roof. So essentially, we could get if you just do it a little bit more carefully, we could get much more data. Another reason why I'm not really worried too much. Looked, of course, I'm at the Marine School, driving over the Rickenbacker Causeway almost every day or twice, and I see some blue dots there. So there is a little bit of subsiding, but it's still standing. So they don't collapse so frequently. Also, it doesn't collapse. A blue dot doesn't mean it's going to collapse immediately. Some other interesting observation. There was last year, there was some concerns. The Broward County Courthouse, it was closed for a couple of weeks, and we do see a signal. So there were some structural concerns. They found some cracks in the building, could be related. And some other place, what I don't understand at all is where we have a significant signal. So I didn't show much from further north, but maybe somebody knows something about this area, the Taylor Birch State Park, that is in Broward, a little bit further north. There is it's a state park. There's no high rises here, just single family homes, and nothing happened there for quite a long time. And then suddenly, end of 2021, end of 2020, subsidence starts. In the Googling it, I see something about seawall repairs. So maybe they vibrated for those seawall repairs. It's really a mystery. I really would like to know what is the reason. But so, okay, now let me just come very briefly to the end of my talk, to the other subject, the mine blasting right here in the Miami Lakes, in the Lake Bend mining district. When I drove here, so it's something like, the biggest quarry is White Rock. It's something like somewhere over here, something like 10 miles north. And there are some quarries, of course, very close by here from FIU. And so what's going on there for those who are not aware? There is this is these lakes. They are mining limestone. How do they do it? And this is there since a long time. This is actually there before they started mining, much earlier than the development started. They started in the 70s or 80s or something like that. As while Western Miami-Dade or Miramar in the north, there was Miami Lakes. All these places didn't exist at the time. So for the mining, what do they do? They are drilling the holes. They are putting explosives in there. Then they explode, and then this part of the rock will fall into the lake, and then with one of those excavators, they'll just drag line. It is called giant thing. They are pulling the limestone out, and then it is used for construction. It's very important for the Florida construction industry. And people in Miami lakes, they are complaining about that since long. They're complaining about earthquakes, seismic shaking, and damages. And these are some examples. In Miami lakes here, this Sopan, this driveway or this walkway in this case, it used to be straight, and now it is broken, was fixed. Here an example of some cracks in a house. And this one here, it's very indicative about what's going on. This is a little bit higher, or it stayed high. Here it subsided. Not much, couple of centimeters. We have our InSAR data. The InSAR data showing a few blue dots. And so what's going on at those blue dots? There was no subsidence or nothing going on for a while. And then in this case, June 2019, this suddenly subsided by 0.75 centimeters. And so this is probably, we don't really know 100%, but probably related to the mine blasting. So the residents feel it strongly. They complain about it. I don't know whether anybody of you has felt those things or lives a little bit further north where people feel it. Here a couple of more examples. There 0.5 inch displacement at some time, and even the schools, there we see more. Everglades High School, there we see more significant displacement, one inch, just a couple of pixels. The other ones, the neighboring pixels, don't show it. Another elementary school in this case, almost an inch. So what's going on over there? What are the damages? What you can get from vibrate? What are the damages you can get from vibrations? You can, similar to an earthquake, what can happen is that if the building is on proper soil, you're getting shaking and direct damage to by the seismic waves. But the seismic waves which are generated, they are not very strong. People feel it, but there is something, the legal limit that's it's measured in inch per second, 0.5 inch per second is the legal limit. And the mining companies stay below it. You never get such a strong shaking. So they say, okay, it's not us. It's your buildings are poorly built, or your driveways are poorly built. But then there is other mechanisms, and one is due to dynamic settlement. So we are having the seismic waves. So it's not direct effect from the seismic waves. You're having the seismic waves going through the underground, and then you're getting dynamic settlement. The sand adjusts, or whatever soil you have, it adjusts, and you're getting the subsidence as a or some movement as a result of this. In this case, the whole building moves, so there's no differential settlement, but you can get differential settlement also. And I think that is what is going on in the Florida, and the code or the rules for the mining that is not considered, so the mining companies can continue. And so this is pretty. I think this picture is pretty strong evidence of what's going on. We are having it yeah, the uppermost 2.5 meters is the peat or the mud layer. And yeah, the seismic waves go through this peat layer, has lots of water in there. And yeah, then somehow the water gets pressed out. It didn't, this thing here, it was built maybe to some greater depths, so it didn't subside so much. So it is related, similar to well-bore protrusion, what we see in different other subsidence areas, but this area around, okay, it is affected. And so when they built those houses, they yeah, of course, the whole area, Miami Lakes, Miramar, it's actually okay, beautiful lakes, and they excavated the lakes, and then they used the material. Partly it was mined before, and partly material was taken out of the lakes to build strong foundations. And then, yeah, put material up, and then it was consolidated. But that just happened under the houses itself, not necessarily next to the houses. So where the driveways are, this probably didn't happen. And okay, so this is a study. Well, we have it's not completed. If anybody has interest or knows something about it, okay, I am happy to hear that. Okay, thank you very much for your attention.